Hello everyone and welcome back to this online NPTEL certification course on aquatic geochemistry. We were discussing on the water sampling techniques in our last lecture, and in this particular lecture we are going to talk about the instrumentation. So, when we are collecting samples, we take them back to the lab, then to generate the data we would be needing instruments, right. So, instruments is the bridge between the water sample that you have collected and the data that will be generated. Okay. So, whenever you have samples, different kinds of analysis has to be done. So, we already discussed that there are major cation analysis, major anion analysis, then there can be nutrient analysis, isotope analysis. For different data sets it will be different. Okay. So, for dissolved it can be a different technique, okay, different methodology that the sample has to undergo to prepare it for that kind of analysis. And if it is sediments, again it will have a separate method for being prepared for a certain kind of analysis. Okay. For instance, when you are doing sediment digestion, okay, there will be different digestion techniques, right. Now, depending on if you are doing acid digestion, that is the most preferred one, because if it is a lot of organics are there, if there are a lot of heavy minerals are there that are difficult to digest, a lot of time can be consumed. So, we generally add acids to make it digested. So, always we do acid digestion of sediments. Okay. So, to get the entire sediment into soluble form, we are going to do this digestion. Okay. So, you have this sediments collected, you will measure a certain amount. Okay. So, it can be 25 milligrams, 50 milligrams, depending on what kind of analysis you are doing, you are going to measure it. Okay. Then there will be an entire analytical procedure. Okay. So, for instance, if it is metal analysis, okay, concentration analysis, then you will digest it, and that digestion can be of multiple steps. Okay. So, you may have to add nitric acid once, you may have to maybe add hydrochloric acid, sometimes you may add HF. So, depending on what your sample is, you have to fix your analytical protocol. And for river sediments, it is generally a mixture of acids. So, some HCl, HNO3, HF mixture, and that we have to repeat until and unless the entire sediment gets digested, that means it turns into soluble form. Okay. So, that we call is the digestion step, and this will not happen at room temperature, right. So, for that we need a hot setup. So, you can see here is a hot plate, okay, on which beakers are kept. Okay, these are not glass beakers, these will be plastic tightly capped beakers. Okay, and we have to take a particular volume of it, then we again have to dilute it, or there can be elution or something, and then only finally after a lot of preparation it goes to the instrument. Okay. So, generally we measure the elemental concentration using an ICP-MS. Okay. So, it stands for inductively coupled plasma mass spectrometry. Okay. Now, this is what we do when things are in liquid state. For gases, again it is an extremely variable, depends on what gases you want to analyze, it can be a different instrument, right. So, why do we need instruments? Because they allow us to have precise and accurate chemical analysis. Okay. Say for instance, we are not trying to use any test paper strips or colorimetric paper strips like that, based on which we need our values. When we are measuring concentration of a particular metal, or we are measuring the concentration of a particular nutrient, or and especially if it is isotopes, we need a lot of accuracy and precision in our data set, right. So, since accuracy and precision is the fundamental pillar, okay, of our data, and therefore, the science that we are going to do, therefore, instrumentation is an extremely important aspect. Okay. If you do not have the right kind of instruments, you know that you do not have the right kind of data, and therefore, your science, the interpretations that you are going to do will have limitations. Okay. So, your instrumentation allows you to have more accurate data, and therefore, more accurately you can publish it, your publication process will be easier. Now, laboratory instruments are generally more robust and more accurate than field based sensors. Okay. So, even if you see that sometimes for a measurement, sometimes they will be measured on the field. Okay. Say some sensors which can measure nitrate will measure the nitrate using the nitrate sensor in the field. Same thing you can come back and do it in the lab. There will be some changes in the values, but otherwise it should have a good, if it is a good sensor, it should be quite doable. But having said that, the sensitivity of different sensors are different. Okay. Certain sensors can measure only up to a certain level. Okay. Beyond those certain level, it cannot be used. So, for instance, we discussed about having handheld multi-parameter probes. In the last lecture, we were seeing some pen probes, we were seeing some cabled with attached cables, some which can be fixed onto the spot, that is in situ sensors. So, all those have a fixed range of analysis, right. So, we have that set range, and whatever falls within that range, we say we are confident on that particular value. But if the sample had a much higher concentration or a much lower concentration than those said ranges, then it will become difficult for us to say whether that particular value with confidence or not. Okay. So, we will lack confidence in those cases. Now, what happens in the lab is that whenever you do an initial analysis, after seeing the data, you can always try to dilute it if it is very high concentration, or you try to enrich it. Okay. So, different methods you can apply, okay, such that you get to the right data. Okay. So, laboratory data, you can do many times of experiments to get to the right data, okay, which is not possible always in the field. In the field, we have limitations, we can a lot of chemistries cannot be done in the field itself, and has to be done in a cleaned, in a controlled setup. Okay. So, apart from few physicochemical parameters and certain parameters like commonly done are nitrate, sometimes phosphate, sometimes some other parameter for which the probe is very well calibrated and very accurate. If it is there, then we can use it. And of course, for every time we are using a probe, it has to be calibrated. So, within that calibration level only we can do our measurements. That becomes a limitation in the field. For example, when you are calibrating a probe and making the measurements in the field, if your range of that particular sample is beyond that calibration range, you no longer have the ability to recalibrate your probe, right. You need the entire solutions, all the calibrating solutions and all that. So, for that laboratory setup is required. So, we always try to bring back the sample back to the lab and then do our chemical analysis. Okay. And then for handling of the samples, we need some clean protocols. Okay. Say for example, for dissolved, finding out the dissolved concentrations, every vial that you are going to use needs to be cleaned. Okay. And cleaning can take 2 or 3 steps. Okay. So, for that you are not able to do that in the field. right. So, you have to do it back in the lab, and if you have large number of samples, it just becomes impossible to do it anywhere. So, mostly we try and do all chemical analysis back inside the lab. Okay. And every kind of analysis may have a different kind of sampling preparation methodology. Okay. So, the preparation techniques can vary depending on what you are going to analyze. Okay. So, the instruments are varying, the sample preparation techniques are varying. For example, as I have said, if you are looking into dissolved data, if you are going to analyze the trace elements there, then you just take the sample, the filtered sample, then if you are using it in your nitric acid, you add that nitric acid, you add a matrix correction tracer there. So, some things has to be done to the sample to make it suitable for that ICP-MS analysis, and then you are going to put it into the instrument. Okay. But if you are going to do for anions, say for example, you are going to measure the chlorine, the nitrate, not the chlorine, the chloride, nitrate and phosphate and fluoride concentration, then you need not do any kind of acid addition, because acids themselves have the chloride, nitrate as anions, and you are just going to may have to just dilute the sample and then directly run it. Okay. So, for different analysis, different kinds of preparation techniques are there. Okay. I am going to show you some very common instruments that we use in the lab. Okay. So, the first thing I will show you is the vacuum freeze dryer. What happens when we bring a water sample back to the lab? So, there will be sediments we are collecting. Okay. The sediments that is there in the filter paper, they have to dry. Okay. So, there are two methods of drying. One is using a hot source. Okay. So, this is the hot source. Okay. So, you let it dry in the, either you air dry it or you dry it in a hot oven. Okay. So, sometimes we can have other biomass and fishes and plants and all that. So, for that to dry, it is preferable you dry it in a hot air oven. Okay. But certain elements can get lost during the process of drying in an oven. Okay. Their time we have to use this vacuum freeze dryer. Okay. What happens is that the sample is frozen, the sediment samples are frozen with a little bit of water, and then they are put into this freezer, and this works on the principle that the water in this frozen state, that is in the ice state, that will directly sublime. Okay. And what will remain is your powdery sediments. Okay. Now, those sediments will have to undergo digestion for analysis. So, you will generally find this kind of hot plates, which will be Teflon hot plates. Okay. There will be no metals if there is a metal analysis going on. So, your labware should be metal free, right. Similarly, if you are doing organic analysis, there should be no organics in the lab, it should be only metals. So, here if you are doing metal analysis, this is entirely metal free. So, you will only see Teflon ware, and even this hot plate will be coated with a kind of Teflon. So, this kind of special vials are there which can withstand very high temperatures, maximum 200 degrees, certain kinds can go a little bit above 200 degrees Celsius as well. So, therefore, after digestion generally we use a clean lab. Okay. What is a clean lab? It is a clean environment where the air is filtered through specific filters. Okay. So, you will have these filters that are there fixed at certain locations. So, the entire room, the air inside the entire room has filtered air. Okay. It means there will be no particles, there will be no dust, there will be so it is extremely clean environment. Okay. So, now the different kinds of filters can be there can be multiple layers of filters can be there. So, based on those, the classes are created. Okay. So, it can have you can have a class 100 lab, class 1000 lab. So, that means how many particles, okay, will be there in a particular volume of air mass, that decides the class of the clean lab. Okay. And here what you are seeing are the hoods. Okay. We call them hoods, cleaned hoods, okay, where we are going to work. Okay. Here you will see that there will be generally of two kinds. In one particular kind, the clean air will again flow, okay. It will flow through the filter. There will be filters set up all here, and they will be flowing here like this. Okay. So, the clean air will flow outside. So, from here these vents will be there, these hoods, okay, there will be openings here, and through the filter there will be much cleaner air which will be pressurized such that they come out through the openings. So, these are called the laminar hoods. Okay. In the laminar hoods, this chemistry is actually protected. Okay. This chemistry never ever is the air from here will enter this. So, this is at a much high pressure as compared to the room pressure. So, the air will always flow from here to the outside. Okay. Now, whenever in this room also, it so happens it is kept at a high pressure. Okay. So, if you have a door here, okay, you will see that the air will always flow outside and the outside air will never come inside. Okay. So, therefore, pressures are actually maintained, and you will be able to see that in the gas this thing, and certain kinds of other things will also be there to monitor those kinds of pressures. Okay. At other kind of lab hoods, what will happen is there will be an exhaust. Okay. There will be an exhaust, and that will that will take inside the air and it will throw out. So, what happens if you are generating a lot of fumes here, okay, if you are generating some fumes here, then it will take that fume and it will just go to the exhaust. So, those are called the bypass hoods, because they will take the clean air layer will flow and the exhaust will pull that such that the fumes get out. Okay. So, the fumes were, if you are doing some acid work, acid step is there. So, then you work in the bypass hoods, and every time when we are working in the clean lab, then a cleaning this thing we have to maintain. Okay. Our clothes, our head, all things has to be covered. So, we generally wear these suits. Okay. Our shoes also has to be covered. We need to wear gloves. Okay. We need to wear spectacles, special spectacles, and sometimes our mouth may also need to be covered. Okay. So, we need to have an entire gear. So, this is the cleaning room, especially for the cleaning room we have our clothes meaning the lab coat with the shoes cover, with the head cover. Okay. Everything will be there separately, and these kind of rooms we do only very clean work. Okay. And the reason we are going to do this kind of cleaning steps, measure the precautionary steps that we are going to take, okay, such that we are not contaminating it, right. We do not want any kind of contamination from ourselves to the sample. Okay. So, for that we are going to take so many precautionary steps. Okay. When we are going to clean the vials for collecting of samples, when you are going to do any kind of analysis, okay, before that all the acids, they may have to be distilled and your vials has to be cleaned. So, all the cleaning protocols has to be followed, and that is followed only in a clean room. Sample preparation, they may have to be done in a clean room. Okay. So, either it is a clean room or a controlled environment where you do not have a lot of contamination. Okay. So, it is separate from a open space where a lot of people are sitting, a lot of wind is blowing, there should be no open windows, and so it is a controlled environment that has to be there with minimal amount of contamination. And if your if there is some isotope analysis is going on, then you specifically we only and only have to use these clean rooms. So, here you see this is a setup for isotope analysis. Okay, it is a very different method as compared to elemental analysis. For elemental analysis, we do not do this kind of resin related separation. What happens is you have this columns, and you have a particular resin. Resin is a type of material, it is basically a type of chemical material powder that will have an affinity for a particular kind of element, and that will separate it from the other elements, that is we call them the matrix. Okay. So, for different elements different resins are there, and using different solutions, there may be acidic solutions or different kind of solutions, the particular element that you are going to do isotope analysis, you are going to separate it. Okay. So, the chemistry, the separation chemistry for isotope analysis is different for every element. Okay. For no two elements is the chemistry same. Okay. Because it depends on the elemental affinity with that particular resin, at what particular acid it has to get removed, and at what particular solution strength of the solution should it remain attached to the resin, and all that elution process that we say in terms of chemistry, that elution protocol has to be done, right. So, these kind of analysis can actually, chemistries can take actually a lot of time. It can take from 3-4 hours, it can take the entire day, it can 14-15 hours, or it can stretch to even 2 days. All right. So, the chemistry for every element can be highly variable. The recipe, we call that a recipe, it is like cooking. Okay. The isotope separation, the column chromatographic separation for isotope analysis for every element, okay, it can be highly variable. Okay. The time taken will be very different, the procedure will be very different. So, when we are going to do those kind of analysis, we very strictly follow these kind of protocols and these kind of the materials that we are using to get to the right data. Then some other instruments, common instruments that I am talking about. So, an ion chromatograph for major cation analysis, for major anion analysis. Okay. So, this is very common. Wherever you find a water quality lab, you will see an IC will be definitely be there, and wherever possible you will also find this instrument which is called the ICP-MS, that is the inductively coupled plasma mass spectrometry, that is used for elemental concentrations. We are going to determine the elemental concentration using this ICP-MS system. Okay. Then spectrophotometer, whenever you are going to analyze something which has a colorimetric method, then you are going to use this instrument called a spectrophotometer. Now, spectrophotometers are of different kinds, they are of different ranges, because it is using wavelengths. It can be from variable from the infrared to the UV range. So, different parameters are they are absorbed at different wavelengths. So, depending on what wavelengths that particular parameter will be measured, that is how it we apply the spectrophotometric methods accordingly. The instrument is chosen accordingly, again similar to ICP-MS techniques for every for every element. Okay. The method can be very different, and not necessarily all elements are measured using a spectrophotometer. particularly we measure nutrients, we measure organics using spectrophotometer, because the colorimetric method suits them and they are more accurate. Okay. For metals, what happens is, in natural waters, if the concentration is low, then it becomes very difficult to distinguish, right, between the two samples. Okay. You need much higher level of sensitivity for metals. Okay. But for nutrients, the sensitivity, even if it is a little low, still gets measured. That is what we have seen, that the concentration of metals is far less as compared to nutrients and organics, and therefore the for metal analysis, the instruments have got really very high sensitivities. Okay. The sensitivity and the instrumentation has really evolved, and particularly for isotope analysis, a lot of instrumentation has to be had to be technologically wise. It has to become more and more evolved to give us such kind of accurate and precise data. And when I will talk about isotope geochemistry, you will see the numbers at what level that we are looking at, because sometimes we are looking at very low concentrations. If I am talking about ppb level, that is parts per billion level in concentration, just think that we are measuring isotopes, right. Some of the isotopes can be less than 1% of so the different isotopes have different abundance ratios. So, the abundance ratios can be highly variable, right. So, we are going to measure in those abundance ratios. Okay. So, for that we need a lot of lot of accuracy, a lot of sensitivity to even a small amount of if the analyte is there. If the analyte means the thing that we are going to measure, if the analyte is there, we should be able to measure it. So, therefore, our technology should be able to support that kind of sensitivity. In today's technological world, we have that kind of capability, and therefore, a lot of instruments, a lot of different techniques have been evolved. An XRF here is on the right side we have an XRF. An XRF measures the mineral content and the elemental concentrations in the sediment form. Okay. So, you take the sediments, we do not digest it, it is in the solid form. Okay. They will make a different kind of preparation technique is there, but you are going to measure the oxide content and the different elemental concentrations in the sediments. For that you can use the XRD, the XRF, or if you want to use the SEM. So, for sediment analysis, different kinds of instruments are there. Okay. But if it is digested, then can again go to the ICP-MS. Okay. Now, how are we going to measure the data, right? If we have an unknown sample, okay, if we have an unknown sample, we just not be running it into the instrument. It is not going to, it has to tell us according to something, right. So, what we do is we do a calibration curve. Okay. Now, before I talk to you about calibration and all that, there are two important things that we are going to talk about, and that is blanks. Okay. So, when we are collecting field samples, right, we also collect something called a blank sample. That means, we are collecting the sample in a bottle, right. Now, bottle has to be cleaned. Okay. That means, if you are measuring trace metals, the bottle has to be cleaned with acids. Okay. If the bottle is going to take anions and all that, if you are going to, for that bottle, that has to be cleaned with soap. Okay. And it has to be thoroughly washed multiple times. But somehow, due to of course our human errors, there might be something in the bottle, sticking to the bottle, and during our journey to the field and back to the lab, many things can happen, okay, during our travel. So, we what is instructed is that using a cleaned bottle, you carry a distilled water, okay. Either it is distilled water or what we called is a milieu water, okay. So, point is you carry very ultra clean water as a blank sample. What is it blank means? That means that ultra clean water has nothing, okay, has the lowest concentration of all the elements of whatever you are measuring, okay, everything is lowest in that water, okay. So, that value we call it as a blank, okay. So, there can be field blank, okay, or there can be what is it called, procedural blank, and different kinds of blanks are there. So, the first type of blank that we will talk about is the field blank, okay. So, field blank is you take a clean bottle, you fill it with milieu water, okay. The term is milieu, okay. So, you can make a search and see. So, it is basically ultra clean pure water, okay. So, this has the lowest, this is supposed to have the lowest concentration of all the solutes, okay. So, this should have minimal concentration. So, basically if you are measuring this water, you should actually get nothing, okay. So, that is our milieu water, and you take it into the bottle and you carry it into the field, you go through the entire trip, you come back and you measure that water. If there is any values, you will know that there is contamination from other things, okay. There is some exchange either to the bottle or somewhere something has happened that has changed the value, okay. So, there is a field blank, okay. Then there is something called the reagent blank, okay. What is the reagent blank? Okay. The reagent blank is when you are using an acid, when you are using water for different kinds of processes, okay, they themselves might add onto certain solutes, okay. Say for instance, your analyte you are going to measure is sodium, magnesium, potassium, calcium, okay. Now, these elements are everywhere, right, they are everywhere in nature, okay. If you are going to add HNO3 to your sample, then in that HNO3 some trace amounts of this will be there, okay. So, when you are adding this to the sample, your sample, this looks like a contamination, okay. So, what we do is we add a reagent blank, that means to a milieu water, okay, to the milieu water you add the acid only, whatever you are adding to the sample, you add the same thing to the milieu water. So, that becomes your blank. So, this is your reagent blank, okay. And similarly, there is also something as a procedural blank, okay. Now, procedural blank is every sample preparation, it might be a single step or there might be multiple steps involved, okay. One add this, then heat this, then evaporate, again add this, again evaporate, again add this, again heat it, evaporate this. So, during the entire process, okay, certain contamination can come, okay. It can be through air, it can be through your handling, it can be through the vials and the beakers that you are using, it can be from the reagents that you are using. So, that everything you have to take account of, okay. So, what you do is you take one empty beaker and go on doing the same thing, okay. Consider a milieu water as sample, and through the entire step of analysis of sample preparation, you go on doing the same thing to that sample, okay. So, that becomes your procedural blank, because for every step that particular milieu with the vial, okay, that vial that you are using, that becomes like your control. Okay. So, you are going to add all the reagents, you are going to evaporate, heat, whatever you are doing, do the same thing for all the steps, okay, all the steps that is there in the preparation technique. And then finally, when you are going to measure it, you measure it as a normal sample, and that becomes your procedural blank. Okay. So, there is a field blank, there is a reagent blank. Reagent blank means whatever nitric acid, whatever acids, whatever reagents is going to get, you are adding into a sample, that you are, adding into the vial and you are measuring that. Okay. So, that is your reagent blank, and then finally is your procedural blank. Okay. So, throughout the entire process of sample preparation, whatever you are doing to your sample, you take another similar vial, but only use ultra clean water or milky water instead of a sample, and you do the same thing. And then you know that whatever steps that you have followed, how much contamination has that done to the sample. Okay. And not only one, we do this in triplicates and multiple sets, so that we have better understanding of the contamination. So, with this I will end this lecture today, because I have more things to tell you about standard calibration and standard addition. We will discuss this in the next class. Thank you.